Okay, welcome everyone to Harvard CMSA Quantum Matter in Math and Physics seminar. We are very honored to invite Haoyu Guo to speak his recent work. He will be speaking about large N theory of critical Fermi surface and strange matter. Okay, welcome everyone to Harvard.
Thanks, Juwan.
And let's welcome Haoyu. Please feel free to ask questions. Sorry, there was interruption from somewhere. Yeah, please go on.
Okay, yeah. Thanks, Juwan, for the introduction. So today the title of my talk is I want to talk about some large N theory, our recent large N series of a critical Fermi surface and some related transport properties of it. So you might have heard that one of our team member Arxiv has given a talk earlier this year. So this talk is also related to that. And then so actually the results of this talk is already in the paper that they have posted in March. But then they were all put in the appendix, and then we know that no one is going to read the appendix, so we decided to pull it out and then write a separate paper for it. Right. So let me introduce our team. So here is Subir, who is my PhD advisor, and then Arxiv, who is now Flatiron, and Ilya who was a postdoc at Harvard, and I think right now is moving to Wisconsin. Right. So let me just start by talking about like what is and what is not a Fermi liquid, and then so I guess most people here are pretty familiar with the story of a Fermi liquid. So basically, you have a real particle, but then in the interacting material, the particle might get dressed by various things and become a quasi-particle. And then a classical example that for Fermi liquids seen in the textbook is try to calculate the lifetime of a quasi-particle, say in a Fermi liquid. Then the usual argument is actually just to count the phase space that's available for this quasi-particle to scatter, and then you can conclude that the lifetime of the decay rate of the quasi-particle will go as like its energy squared or temperature squared. And to put a to give a more practical definition of a Fermi liquid, so let's just say that we want to have some fermionic quasi-particles in our system, and then near the zero energy, of course, there should be a Fermi surface. So the decimal states of the quasi-particle should be non-zero. So I'm talking about 2 + 1d. So the decimal states will go like a constant as the energy go to zero. And also the lifetime of the quasi-particle should be very long. So its a decay rate should actually be much smaller than the energy of the quasi-particle. Sorry, here I got it backwards. Right. And then related to Fermi liquid, and there is also something that's not a Fermi liquid, which is just given the straightforward name non-Fermi liquid. So there is no quasi-particle in a non-Fermi liquid. So when you write down theory, you start with some fermions. So you saw those things could be a quasi-particle. So they will still have some kind of Fermi surface which has a non-zero density of states. But then if you look at its lifetime is actually it's actually much shorter. The decay rate. Sorry, this again back got it wrong. So this decay rate should actually be much larger than its energy. So the energy of the quasi-particle is no longer well defined because it decays much faster. And then in between the Fermi liquid and the non-Fermi liquid, we have something which is called a marginal Fermi liquid, which we will believe could describe some phenomenology of, say, some corporate superconductors. So basically, a marginal Fermi liquid is something in between. Is that you still get Fermi surface with a non-zero density of states, but then if you look at its lifetime, it's kind of comparable to the energy of the particle itself. So it's a decay rate 1/tau will scale as linearly as epsilon. There can be some logarithmic corrections, but in terms of power law, this is the same.
So what would be fermionic quasi-particle in the second line?
Sorry.
So can you explain?
Would be quasi-particle, you mean?
If you, I mean.
Right. So this just means that when you practically deal with some non-Fermi liquid series, you always start with some fermions that has a Fermi surface, but later you need to. So if there's no interactions, this will be a quasi-particle. But then later you need to destroy those quasi-particles. So this is why I use the word will be here. Yeah.
So you're saying that this theory is adiabatically connected to a theory with Fermi surface, but as you go along the flow, the lifetime of the quasi-particles goes to 0.
Yeah. So this is just a practical way. Of course, this is not the best definition of a non-Fermi liquid, but just like practically we do it like this. Yeah.
Okay.
Yeah. And then this Fermi liquid, either Fermi liquid or non-Fermi liquid, we are just defining it using it's a single particle property, like by looking at its self energies. But then related to that, it's another thing which is called strange matter, which is more or less related to experiments in cuprates. So this work is also motivated by the strange metal physics in cuprate superconductors. So this is the phase diagram for cuprates, and then basically the interesting physics happens when you have a competition between the antiferromagnet and in a crossover regime from antiferromagnet to a Fermi liquid, and then so at this there's a critical. People believe that there is a quantum critical point in the system at a critical doping PC, and then if you just raise temperature above this quantum critical point, you'll get into a region which is called a strange metal. So in the string, the strange thing about strange metal is that if you look at measure its resistivity, it's actually linear in the temperatures, and here are some experimental data from cuprates. So this is of course very different from what a Fermi liquid theory will describe, which says the resistivity will raise as a power of t squared. But then here is linear in t, that down to the lowest temperatures that people could measure. Stop. Yeah, and the thing related to that is there is a concept which is called a Planckian dissipation for a strange metal. So it refers to the fact that if you try to interpret the data for the resistivity, you're using a Drude formula, and then and then you take the effective mass to the one that you measure from say quantum oscillations or other experiments. You actually find out that this transport decay rate tau inverse, it actually scales like over as a kBt over h bar. And for example, it is verified in this experiment using ADMR. So what they found is that they map out the decay rate as a function of the direction of the quasi-particle. So they found an isotropic part and an isotropic part. Then to this isotropic part, what they found is that it actually satisfies this Planckian dissipation. Right. So yeah. So here is what we think should be a phenomenology of a strange matter that is described by the transport properties and the thermodynamics. So the first thing is that the resistivity of the system is go as linear in T at the low temperatures. And another requirement is that this resistivity should be small than the quantum unit of the resistivity in 2 dimensions. There are some other models which can realize a linear in T resistivity which is above the quantum unit. But for that kind of system, it is called a bad metal instead of a strange metal. So because in those systems, they're usually highly disordered, and you cannot define a Fermi surface in those systems. And another thing you could see is say from its thermodynamics, the heat capacities at low temperature will have a log singularity, which goes like a T log 1/T. And another transport properties you could describe is actually the optical conductivity of the system. So you could write an optical conductivity use some kind of a modified Drude formula. So there is a constant, there's a weight k, and then there's a decay rate tau omega inverse, and then minus I omega times some modifications from the effective mass. Then for strange metal, it is conjecture that this decay rate 1/tau should actually satisfy the following scaling form in terms of temperature and frequency. So it should scale like linearly with temperature, and also the frequency dependence should satisfy a omega over T scaling. Yeah, and in this reference, this is a recent experimental data from Louis Talebot's group. So what they have found that if you look at what they found is that they have measured the optical conductivity, and then performed a scaling collapse analysis for this decay rate tau. And they actually found that at different temperature, there is a good scaling collapse. And related to that, they also found a power law in the optical conductivity with an exponent nu, which is close to 0.8. So at first sight, you might think this is strange, because if it's a Planckian dissipation, it should be linear, so the exponent should be 1. But actually, this is actually, this is there's actually there's no contradiction, because this 0.8 exponent is actually can be actually derived from the following scaling function using using the Fermi-Pronic relation. Yeah, so actually, so basically, in the recent experimental data, such kind of a scaling form has been verified. Right. Yeah. So right now, let me start talking about our theory. Yeah. So let me try to talk about what kind of ingredients are in our theory. So the first ingredient is that we want to have a critical Fermi surface. So its definition is the following: is that first we have some kind of a fermionic fields which could have a Fermi surface, and it's just given by this simple action. And then secondly, we want to destroy the fermionic quasi-particles of this psi field. So the easiest way is to couple the system to some fluctuating critical bosons. So here we call it phi. So first of all, this boson could be many different things. For example, it could be some isokinetic order parameter. It could be some ferromagnetic order parameter, or it could be some components of the emergent gauge field. So I think the only assumption here is that the this quantum criticality is at zero momentum. So it's a Q equal to 0 quantum critical point. It's not finite Q quantum criticality. And then we'll try to couple these two sectors together. Yeah. So the second ingredient.
I have a question.
Sorry.
Slides back, the property of a strange metal.
Yeah.
2 slides
Right.
back.
Yeah.
One more. Yes. The right figure is the angular part of the conductivity. Is that right? No, just the next slide.
Oh,
Yes.
Yeah. This is the norm of the optical conductivity. This is the angle in the complex plane.
So what does that information reveal? The one with this phase.
So basically, you can show that at large frequencies where there is a scaling behavior that they could actually get a power law in this optical conductivity, and the exponent is 0.8. Yeah, in these two figures, like either you look at real part or it's imaginary or it's a phase angle, you all get the same exponent.
Yeah, look, I don't want to jump into this, but yeah, sorry. I don't want to jump into this, but it can be universal behavior, but it's equally can be some high frequency intermediate asymptotics that looks like a power law. And there were several attempts to explain experiments from both ends, either as a real power law or as some intermediate asymptotics that looks like power law. So I think we should move.
Yeah, I agree with you, Andre. In fact, the paper mentioned here by Michel et al. Argues that, in fact, there is no power law, and this apparent power law is due to the logarithm that arises from the Kramers-Kronig transform of the 1 over tau.
Exactly. Yeah, exactly. So I think we should move on with this. Yeah.
Yeah. Okay. Right. Yeah. So the second thing we need for our theory is to couple the fermions and the bosons strongly with some strong interaction. So, for example, the toy model people usually write down is just to write down a Yukawa coupling between this the fermionic field and the bosonic field. So just to compare the theory to compare this thing to some more conventional style story, which is well understood. For example, you could actually compare the problem of electron phonon scattering, which also is a fermion coupled to a boson. So in this story, people calculated that at very low temperatures, the resistivity will go like a T to the 5th. So this is what is called a Bloch's law. So actually, in this calculation, they basically assume that the fermions are scattered by the phonons, and then the phonons it is just gone, and it is dumped into the environment. So this kind of calculation actually ignores the conservation of the momentum of the total system, and also the fact that the feedback of phonons to the electron system, so which is called a phonon drag. So this approximation is relatively good for electron phonon system, because the electron phonon system is usually weakly coupled. But then in our problem, in such a non-firm liquid, the coupling between this fermion and boson is actually a strong coupling problem. So you should not try to separate these two sectors out, and you should consider them together, because like individually the fermions and bosons they are all not well defined, and you should consider them all together as a single component. So there is a very strong drag between the fermions and the bosons. Yeah, and then another ingredient that we need to actually get a theory for a strange metal is actually we actually need to introduce some disorder into our system. But it's not the usual kind of disorder that people who expect, which is a disorder potential for fermions. But here we actually need a disordered interaction for the Yukawa coupling between the fermions and the bosons. So actually, such kind of disordered interaction, it can actually be motivated by the experiments in group waves. For example, in this experiment, they found that the superconductivity of cupra is actually heavily influenced by the disorders in the system. So we could say that like the four particle interaction, the four fermion interaction is actually disordered. And actually, starting from a four fermion interaction, you could just perform a simple decoupling, and then you could actually derive such a disordered Yukawa coupling between the fermions and the bosons. Yes. And yeah, after talking about those three ingredients, then you should try to combine the things together. So actually, so this problem of a critical Fermi surface has actually been studied for many years, and it is known that this problem is very hard to deal with. So here I've listed some previous attempts, and for example, so the earlier attempt was to just do a large N expansion for the problem, where you suppose there's n flavors of fermion and one flavor of boson, and it is pointed out by Syq Lee that this theory has an IR divergence. So to actually sum this theory, you need to sum all the planar diagrams, planar Feynman diagrams, which to me seems like doing string theory, which is very hard. And later there are some other techniques that try to regularize the theory. For example, you could change the dispersion of the boson from Q squared to some other exponent Q to one plus epsilon. But then for this kind of interaction, this kind of a boson dispersion, you actually give up the locality in real space, because such kind of action cannot be write down in a lattice. And some other ways, for example, you could do some dimensional regularization of the Fermi surface. But then by doing that, you actually loses another emergent locality, which is in the momentum space. And there are some issues related to UV-IR mixing. And as we'll see later, the things that I'm going to talk about actually is actually very unique to a 2D Fermi surface. So right. And another regularization technique is to tune the codimension of the Fermi surface and tune the dimension of the whole space-time. But then that kind of approach also has some issues. For example, if you're away from the Fermi surface, you actually break the U1 charge conservation. Yeah, so for our attempt on this problem is actually inspired by the Syq model. So to just briefly summarize, the Syq model is a full fermion model, which at first sight seems very hard to solve. But then what comes out to save the day at the end is that we introduce some randomness into the problem. For example, by making this full fermion coupling, a UABCD, a Gaussian random number, it turns out that you could actually sum all the diagrams you using in terms of Malan diagrams, and then write down a self-consistent set of equations for the Green's functions, and actually solve the system. Yeah, so for this critical Fermi surface problem, the formulation is the following. So we'll introduce what is called the Syq Cover Theory. So what we do is we borrow the experience for Syq models by making the Yukawa coupling a random number in the flavor of the particles. So we have extended the flavors of the fermions and the bosons to have n flavors, and we make the coupling between them as a random number in the flavor index. And then after that, we could just follow the tricks in Syq models by performing a sample average of the theory, and then the equations we will obtain turns out to be easier to handle. Another thing I want to emphasize is that this thing, although it's random, is actually only random in the flavor space. So it is in the real space, it is still translationally invariant. So we still have a momentum conservation and a well-defined Fermi surface. Yeah, and then starting from this, there are actually I'm going to talk about 3 different theories that we can solve to different degrees. So the first thing is to just have a translational invariant system with the Syq Yukawa coupling, and then for this system we'll find that it's actually a non-firm liquid, but it's not a strange metal, so it doesn't have linear anti-resistivity. And then it turns out that to get some large resistivity, to get a finite DC resistivity, you actually need to break the translational symmetry. So by adding some, for example, by adding some disorder into the system. So the first thing we have tried is, of course, the more conventional choice is to add some potential disorder for the fermions. And by looking at this theory, we actually found that we can get a marginal Fermi liquid in the self-energy. But when we actually compute the transport properties of the system, it actually turns out that the marginal Fermi liquid, the self-energy, doesn't survive in the transport. So it is not a strange metal. Then so this leads us to our final proposal, which was also talked about by Avishka earlier, is that we need to introduce a interaction disorder, that the Yukawa coupling G prime should be random, should have some random component in space. So for this kind of theory, it's both a marginal Fermi liquid and also a strange metal.
Oh, excuse me.
Yeah.
I have a question. Just make sure. Earlier, say disorder within the flavor space, maybe one slide back.
Yeah.
But I think a few slides earlier, you also have a disorder in the full space, right?
So to get a strange metal, you would need some disordered interaction.
Yeah,
I think this is the third theory I'm going to talk about, but the common ingredients of all the 3 theories is this translational invariant coupling, the random in flavor.
So is that still compatible with the disorder in the space? Or
These are 2 kinds of separate couplings. You will, for example, in the source area, I would just write them together.
I see.
Yeah.
He will show the action for the disordered space later.
So for the SYK type of Yukawa theory, you will still keep the disorder only in the flavor space, but not in the space, only in the flavor, but not in the space, the real space. And you will introduce.
So the zeroth order problem is translational invariant. So there's only some randomness in the flavor space, which you could think of as some kind of a new trick to do a 1 over n expansion for the problem. Yeah. So let me talk about the first theory.
Sure, but whether the third case that you do is SYK Yukawa interaction, that the disorder, the Yukawa coupling also has disorder in the space, the real space. Or that will be okay. That's all. Thanks. Yeah, thanks.
So let me talk about the first theory. So just write down the action again. So this is just 3 components. You get a fermionic field with a Fermi surface given by epsilon k. You have a critical boson, which is some dispersion given by this omega q squared. And also there is a Yukawa coupling between the fermions and bosons, and then we make it random in the flavor. Yes. Then starting from this theory, you could do the usual trick of try to perform a disorder average of the problem, and then it can be shown that it's the leading large order. It doesn't make any difference to treat this disorder as a annealed or quenched. It's the leading large order is the same. Then you can derive the setup point equations for the self energies, and then given by these two Feynman diagrams. And then these equations derived are actually probably were familiar to people if you know about the Alexbrook theory, which is to ignore the vortex corrections in these diagrams. So and then after you have written down those set of point equations, you could they can actually solve the analytically in the low energy limit. And the solution we get is also consistent with the Alexbrook theory. So, for example, the dynamical exponent of the boson is equal to 3, and then the fermion subenergy scale is omega to the 2/3. Then the boson subenergy is just a Landau damping term. Right. So yeah, so let me talk about the transport of that theory. So the transport problem of that kind of theory has actually been studied before, for example, by Xiaogang and Patrick Li about 20 years ago. So they have looked at these kind of 5 types of diagrams, which is a self-energy correction, what's called a Markey-Thompson correction, and the Aslamov locking diagrams. So what they found is that the DC resistivity will scale as like a T to the 4/3, and then the optical conductivity at a large frequency will scale as omega to the -2/3. So this thing is a analog of the Bloch's law in the electron phonon problem. So actually, we did this calculation again, and then we found out that this conclusion are actually not consistent with the requirement of the conservation of total momentum. So it has ignored the effect of the boson drag. So what we found for the result we found for this problem is the following. So for the DC part, of course, because you have translational symmetry, you should get the DC conductivity should be infinite so you get delta function from there. And then for the optical conductivity, so we found that the leading voltage is a Drude term. Then for the correction term, the exponent we found is actually not omega to the -2/3, but actually as omega to the 0s. I think a similar result has been obtained by Sentius group using a different sort of argument based on anomalies of the Fermi surface. Right. So let me talk about how to think of this problem, to actually how to think. So the trick that we have used is actually comes from a very old paper decades ago by the Pringe and Kandelov. So in this old paper, they're studying the problem of electron phonon interaction in metals. But the difference is that the temperature is very high, so the phonon scattering can also be strong. So it's strong enough to actually destroy the fermionic quasi-particles. So for non-fermi liquid, if you look at the spectral weight as a function of frequency and momentum, you can find that in terms of the frequency omega, because this self-energy is large, so it doesn't have this function doesn't have a very narrow peak in omega anymore. So it doesn't make sense to integrate out this frequency variable and then try to define a occupation number for the quasi-particle. But however, there's another variable here, which is psi k, which is the deviation of the momentum from the Fermi surface. If you look at this thing, the variational scale of the psi k is actually very large. It's at the scale of the Fermi wave wave vector, which is pretty large. So in terms of the psi k, this peak here it can actually be resolved as a narrow peak. So therefore, it still makes sense to, for example, we could define another sort of a kind of a reduced distribution function by integrating out psi k. So and the remaining variable is just the omega, which is the frequency, and also theta k, which is the angle on the Fermi surface. So we expect that you can try to describe the system. You're using some effective variables like this one. And then so the trick we learned from this early paper is that we should try to project the problem onto the Fermi surface. then the difference is actually that from this electron phonon problems that there should be some additional consistency requirement for the bosons as well. So I'll talk about this later. Yeah. So for following the spirit of Prince-Karnoff, so we could only consider states that is on the Fermi surface, and for stability, let's just consider the circular Fermi surface in 2D. So I just wrote a consistency relation for the bosons and fermions self-energies like this. So that conditions actually. The left-hand side is just a typical momentum of a boson that's getting excited, and the right-hand side is basically a typical momentum of a fermion that is getting excited. So basically, this condition basically implies that it's very hard to excite a fermion out of the Fermi surface, and then that means that the momentum of the boson that excite a fermion should be transverse to the Fermi surface. It cannot be more radial or normal to the Fermi surface. So basically, if you have this kind of if you only assume that there is transverse boson, so then it is fully self-consistent to reduce the whole problem to a set of variables that only lives on the Fermi surface. Then on this Fermi surface problems, you could try to perform a Fermi diagram calculation, but then we actually found out that the result we got could be actually understood from the phase space constraint for the scatterings of those fermionic variables on the Fermi surface. So what came out from a Fermi diagram analysis is that all these three kinds of diagrams, the self-energy diagrams, the Markin-Thompson diagrams, and the Larkin diagrams, they all if you add them all together, they actually cancel, and then we get a result that is smaller than the previous literature. So okay, let me elaborate.
If I can comment, yeah. Can I comment for a second? Yeah, just want to throw away a statement that we discussed in the last couple of days. I completely agree with you. This works for circular Fermi surface and for, I'm sure, for convex Fermi surface, but whether it holds for concave Fermi surface, I think it's a different issue.
Yes, for concave Fermi surface, the geometry of scattering will be different. Yeah. Yeah. So yeah, thanks. So I should emphasize that this only works for a convex Fermi surface. Yeah. So let's look at the phase space constraint that I have talked about. So for example, you could look at a 2-to-2 scattering on a Fermi surface for two particles. So there's first let's look at a generic setting, which is where the sum of the two initial momenta is non-zero. Then you can just it's just combined with the fact that the energy and the momentum should be conserved, and then you could try to look at what kind of solutions you could get on for this momentum conservation on the Fermi surface, and then you could find that there is only like two solutions for this generic case. So you either that it's a totally forward scattering, that the particles the momentum doesn't change at all, or just switch these two particles. But either way, that kind of process it doesn't relax the current at all for the Fermi surface. And then there's another case which has a much larger phase space for scattering, which is what's called head-on scattering. That means that the two initial momentums they actually sum to zero, like they are on the two antipodal points of the Fermi surface. Then for this kind of setup, you could see that if you start with a head-on pair, you can actually scatter to any head-on pair. So and this kind of scattering actually has a large phase space, so it's also very fast. It happens at the rate that's given by the fermion self-energy. However, this kind of head-on configurations of two particles, it actually has even parity. But however, if you look at transport, a current operator will introduce a distortion to the Fermi surface, which is of odd parity. So therefore, the relaxations and the perturbations you get are orthogonal to each other. So the odd parity mode, they still cannot relax. So similar reasonings could apply to any convex inversion symmetric Fermi surface. And such kind of problem has actually been seen before in the Fermi liquid. That's been looked at, including me and also Andre. But it turns out that with this French kind of technique, it can actually carry over to a Fermi surface, to a critical Fermi surface. So it actually turns out that if you actually want this odd parity mode to relax, you actually need to go beyond the French kind of a picture. You need to consider states that's also not on the Fermi surface. That's close, but not exactly on it. Because for the odd parity modes to relax, the relaxation of odd parity modes it requires a radial relaxation of the Fermi surface, which is intertwined with the odd parity dynamics. So following this picture, you could actually write down a kind of diffusion equations for the Fermi surface. Say, for example, you introduce some distortion to the Fermi surface, and you try to look at it how it relaxes. It actually can be written as this kind of a diffusion equation. So normally, this kind of a diffusion picture, you will think that it is a kind of a ordinary diffusion, which is a quadratic in the derivatives. But it turns out that for this case of odd parity mode, the diffusion is actually correlated. It's actually kind of a diffusion problem, which you move two particles together, and then you need to conserve the central mass. So this is a correlated diffusion problem, which what we call the super diffusion in the previous paper. So and actually from this picture you could easily estimate the scaling of this diffusion constant T4. So the diffusion constant, the first vector is sigma r prime prime, the imaginary part of self energy, which is just the rate that those diffusion events are happening. And then you need to multiply this thing by the angular step of a single diffusion. And then you need to raise it to the appropriate power, which is force here. Then for our problem, the scaling of the self energy is like omega to 2/3. Then for the angular step, you could just estimate it from by the momentum of the boson, which is getting exchanged during one angular step. So you can estimate the scaling is like omega to the 1/3. Then combining all this together, you could get the diffusion coefficient actually scales as omega squared. Then if you try to plug in this into the conductivity, you will see that the correction actually goes like omega to the zeros.
Oh, excuse me.
Yeah.
Naive question. Can you clarify what do you mean by R parity modes relax through the states of Fermi surface? So R parity access, how do you do in 2 dimensions? You just flip, is a reflection symmetry only? It's not rotation pi, right?
Yeah, just send k to minus k.
K to minus k for the whole kx, ky?
Good, yeah, yeah.
This will be pi rotation then.
Yeah, it's the same, right? Yeah, 2D is the same.
And what do you mean by relax through the states? Just in detail, say a few more words. Let me just make sure.
Yeah, so for example, in this picture, like this hadron scattering picture that I described here, the only states you have are only those states on the Fermi surface. So for this state on the Fermi surface, what you get is only this kind of hadron scattering. But this kind of scattering, you could only relax the modes with even parity. So for example, what happens here? For example, you have a particle here, a particle here. Here's a bump, here's a bump. Then by this kind of even parity relaxation, this bump can get smeared out and get diffused onto the whole Fermi surface. But then, however, if you have however, if you have an odd parity distortion, then here is excess, here is a deficit, then this kind of scattering will only move this kind of distortion away, but it doesn't kill it. So therefore, if you only consider states on the Fermi surface, it doesn't work. So for this odd parity modes to relax, you need to assume that there are like a state that's close to the Fermi surface that you could excite, and then by you need to go through those intermediate states to actually for those odd parity modes to relax.
What are those states of the Fermi surface? Just like what are those terms or what are the theories? To those states.
So for example, it just means the states with a cosine k that is non-zero. So here here we assume the momentum is also on the Fermi surface. That is we have performed a kind of reduction procedure that's following Prince and Katanov. By first only looking at states with cosine k equal to 0. But it turns out that to have some relaxation of this mode, you need to also look at states with a cosine k that is non-zero.
Okay.
Does that answer the question?
Are those states bosonic or fermionic? If I can ask.
It's fermionic. Yeah. So another thing you could another analogy is just to look at the Fermi liquid. Then the Fermi liquid, that means that it doesn't have any decay at 0 temperature because you can only have scattering on the states on the Fermi surface. But then to have some of this decay, you need to some finite temperature such that you could excite some states that's not on the Fermi surface, but can be above or below the Fermi surface. Yeah.
Okay. Can I interpret your statement saying that there could be some odd parity modes, but somehow through the dynamics, you only care even parity modes? Is that what you want to say? You want to remove up by some dynamics, or due to some dynamics? Or not quite?
No, the dynamics, say if you're in the transport, the dynamics are actually given by the odd parity modes because the currents they have odd parity.
Even you're really saying that current is old parity. So old parity mode cannot relax because of relaxation of even parity modes.
Yeah.
Okay, thanks. I was trying to compare whether it has anything to do with like a, Pesci-Quinn type of statement. But anyway, the parity or CP parity. Anyway, please go on.
Okay. Good. Yeah, so in comparison, let me just to say how to do this in the wrong way. So you will get a thing that looks like a Bloch's law. So basically, that you need to ignore this constraint that is coming from the conservation of momentum. So basically, what you get is that now if you ignore the constraint of momentum conservation, then the dynamics on the Fermi surface will just look like a simple diffusion, which is quadratic. Then you could just estimate this quadratic diffusion coefficient, which scales as a delta theta squared. Then from this thing, you could get a power law for this diffusion coefficient, which is like omega to the 4/3. Then if you replace this thing by temperature, then you get a T to the 4/3 resistivity. And also you can plug this thing into the optical conductivity and get a omega to the minus 2/3 term. But this is how to do it in the wrong way.
Haoyu, quick question. You mentioned T to 4/3 resistivity. What you get for resistivity? Is it T square?
Resistivity is at 0 temperature. I think it is a delta function at any temperature because it's a translational invariant. Yeah.
No.
Yeah. So there's no decay in the DC part. Yeah, it's because there's something for this kind of diffusion operator, it's also conserved momentum. So there is some further terms you need to put in there to make sure it vanishes for the first harmonics, and that this thing will make the DC resistivity is 0. Yeah, so right. So yeah, to get a finite DC resistivity, we actually need to break the translational invariance, for example, by adding some potential to the problem. So the first intuitive attempt is, of course, to put a conventional disorder, which is a potential disorder for the fermions. So basically, we just put Newton this as V, which is a Vij, and then to make a control, we also want to make this Vij a random number, which has Gaussian random numbers in both the flavors and the space. Then when we come to analyze this action, we can still solve it. And then what we get is it's actually turns out to be a marginal Fermi liquid. So first, of course, because you have a disorder here, so you get a scattering rate for the disorder, which is given by this rate gamma. And then this fermion boson coupling, they will give rise to a self-energy, which is a marginal Fermi liquid. That scales like omega log omega. Then on the bosonic side, the criticality has also been modified. It's now no longer z equals to 3 dynamical exponent, but instead it's equal to 2. So the boson self-energy is linear in omega. Yeah, so if you look at the transport properties of the marginal Fermi liquid, what you find, so first thing is that if you have potential disorder, you get a marginal Fermi liquid self-energy. So from this self-energy, you could work out the thermodynamics of a system. So if you look at the specific heat, there will be a T log 1 over T term. However, after we try to do the transport carefully, and then it turns out that this contribution, it doesn't enter into transport. So it turns out that the self-energy diagram actually cancels with the Markin-Thompson diagrams, and what's left is actually only a renormalization of this bare frequency term. So it's like an effective mass for fermions. And then we also look at the ensembles of Larkin diagrams, and then if you look at its effect is also small, so you get a disorder decay rate gamma, and then from this ensembles of Larkin diagrams, you actually get a thing that looks like a Fermi liquid, which scales as omega squared or T squared. Yeah, so we could still try to look at this result of this this marginal Fermi liquid with a potential disorder in the picture of a diffusion problem on the Fermi surface. So in this case, the consistency conditions for the French kernel of approximation is actually violated, because the fermion self-energy now contains a disorder term which is much larger. But then physically, that just implies that the boson momentum now can not only be transverse to the Fermi surface, but also be normal or be radial to the Fermi surface. And then you can, because there is a very large decay rate for the fermions. You can also try to excite the fermion in the radial direction. So for example, if you first just look at the effect of those transverse bosons, you could because right now there's no momentum conservation. You could just use the picture of the Bloch's law, which is a normal diffusion on the Fermi surface. Then right now you could just use the exponents in this problem, and then find out that the diffusion constants in this case it's proportional to omega squared. So that means that the decay rate is omega squared. So on the other hand, we haven't looked at the effect of radial bosons. But if you consider what a radial boson is doing, it will only excite a fermion in the radial direction. But then in the radial direction, you only change the velocity of the fermion a little bit, but then its direction is not changed. So you do expect that this kind of scattering will not introduce any kind of dissipation. So all you care about is a change in the velocity. So equivalently, that means a renormalization of the frequency term in the Drude formula. So this is how you get these two terms separately. So this term is probably by the radio bosons. As you can see, there is a UV cutoff here, which involves bosons that's radio. And then for the Arxiv locking part, you just get omega squared. Yeah. Yeah, and
now you can ask you one question in this regard. It's just not about your work, but about your general perspective. Suppose you consider a particular model which give you marginal Fermi liquid. Suppose I consider a Cook-up model which gives you marginal Fermi liquid for single particles, but the scattering will be mostly umklapp. It's large momentum scattering which goes from one sheet of a Fermi surface to another. Do you think that even in this situation there will be cancellation and omega log omega will not transform into linear anti-resistivity?
Yeah, so for umklapp, I think in this picture you just say that for umklapp because momentum is not conserved, so this delta theta could actually be large. Like the angular step, like for example, could be of order 1 because the momentum is not conserved. So then in this case, this D2 will probably be linear in omega. So I think there could be a linear in T this way.
Yeah. Thank you.
So finally, just let me mention this the last theory which Avishka talked about in February. So I will not say too much about it. So it's a pretty Fermi surface with an interaction disorder. So now we have two kinds of Yukawa couplings. So the first one is the previous one, which is transitionally invariant, and there is a second type which has some disorder in space. So it's a Gaussian random model, both in flavor and the real space. So you could again try to solve the saddle point equations, and you find that both this the transition invariant and the disorder coupling they both give rise to a marginal Fermi liquid self-energy. And then what we found is that in this problem, we actually can get a linear resistivity from this G prime coupling. So on in terms of diagram, just because the momentum is not conserved. So if you look at the vortex corrections for this G prime coupling, you can find out that because the momentum is not conserved, you have to integrate all these momentums, and then by symmetry, those vortex corrections they are 0. So it's not cancelled. So the self energy is not cancelled, and then you could get linear in T. So in the picture of this fermion diffusion on the Fermi surface, you could it's what I said before about umklapp is that right now because momentum is not conserved anymore, you actually lose the locality in the momentum space. So what happens is that this angular step delta theta could actually be any number. So like it can be order 1. For example, the largest one could get pi, but then generically it's an order 1 number. Then basically, then this diffusion coefficient it's only determined by this self energy, which is linear in omega. Yeah. So finally, in the conductivity, you could get the following term. So in the transport decay rate, there is a constant term from the disorders, and then there is a mod omega term that's coming from the G prime disorder, which if you replace omega by temperature, this will be a linear in T part. And there is also a logarithmic in omega part, which is a normalization of the I omega term, and also the kind of logarithmic corrections in the Mitchell and all. Yeah. So in this model, the residual resistivity is actually given by potential disorder, which is V squared, and then the slope of the linearity resistivity is given by another sort of a different sort of disorder, which is this G prime squared. Right. Yeah. Here is a slide for recent that we have a numerical solution of the Schwinger Dyson equation that we have been working on for a model with only G prime couplings, and it seems like numerically we could see a linear NT resistivity at the quantum critical point, and then if you look at the transport rate, it also seems to be linear in omega. Right. Yeah. To summarize, is that we have used a new large N formulation of critical Fermi surface, which could justify the algebraic equations at the leading orders. So what we found is that for the transitional invariant, the non-Fermi liquid, we found that there is an infinite DC conductivity because of momentum conservation, and also the power law that in the previous literature is actually has zero coefficients. Then it's replaced by a weaker dissipation. And then if you try to put a potential disorder to the problem, you will find out that you get a marginal Fermi liquid, but the marginal Fermi liquid self-energy is cancelled, and you will not get a strange metal. And then to get a strange metal, you actually need to put some disorder into the interaction. And then in this case, you could get a marginal Fermi liquid and a strange metal. Yeah, that's all for my talk. Thanks for listening, and I could take questions.
Thank you very much. Thank you, Haoyu. Questions? Comments?
Could I ask maybe a general question?
Yeah.
So you mentioned that a critical Fermi surface in 2 dimensions is really hard. So if you go to higher dimensions, like 3 dimensions, are the results for that more well understood? And if so, does your model reduce down to these other results if you take these large and random models and also go to 3 or 4 dimensions?
In higher dimensions, it's easier because in 3, like for example, in 4D, there's the critical points very easy to understand. You could just use mean-force theory.
Mm-hmm.
And in 3D, it's also the criticality also weaker than in 2D because just the fluctuation of the auto parameter is weaker. So you could so for that case you could just use a Hertz Millis theory, something like that. Wouldn't give you an answer that is too bad.
Mm-hmm. But if you took these large and random theories and just went to one higher dimension, would that reduce down to these more standard results?
Yeah, they would be very different because at least for this part is very different because this thing actually relies on that it's very special to 2D. Like this kind of a kinetic constraint for scattering is only happens in 2D. In 3D, it's you get infinite many solutions.
Mm-hmm.
Yeah. So right. It's so what I'm talking about is very special to 2D. Yeah.
Mm-hmm. Okay. Thanks.
So Haoyu, what's the next?
Sorry.
What's the next step after this?
Yeah, as Andre asked, we could consider like a Wim collab, and then another interesting thing I was thinking about is that can I probe this kind of a super diffusion in a non-Fermi liquid system? Like, is there any way to actually probe this thing other than looking at the conductivities? Because this conductivity, this thing is very easy to get contaminated, for example, by some impurities, because it looks the same as a Fermi liquid. So, yeah.
You, if I may ask, you computed thermal self-energy in the paper.
Yeah.
Mm-hmm.
Yeah.
Question:
yeah,
does this thermal self-energy in any way affect conductivity at finite frequency? If you want to calculate sigma of omega and t,
Oh yeah.
Do you know anything about the result?
Yeah, we actually estimated that. So it turns out that if you add for the transmission invariant model, if you add this thermal part, the branch Kadanoff criteria still works. So this approach still works. So the only difference is that when you look at this thing, this angular step of the bosons, it will be different. It will not be given by this Landau damping, but instead be given by the thermal mass of the bosons. So in this way, the scaling will change, because you might know that the thermal mass actually violates the quantum critical scaling.
And do you know the result, or it's the future?
I know the result. It's written in the paper. I think it's a t to the 5 halves or what.
Okay.
I have another question.
Yes.
So you mentioned on one slide when you mentioned critical Fermi surface without spatial disorder, and you mentioned works by Cento and others use anomaly to argue the conductivity.
Yeah.
Can you
They found some similar result. I guess it's better to ask them to give a talk here. Yeah.
Okay. Maybe Dominic can comment. Is this anomaly the one evolving loop group?
Yes. So yeah, it's related to that. Yeah.
It's related to LU1, but actually it's not exactly LU1. You can think of it as like a linearized version of that. So it's these constraints that we get on transport are generally in patch theories, where on each patch the charge conservation symmetry is U1. So it's closer to like the old sort of cartoon U1 to the infinity symmetry that's been discussed for a long time.
And since maybe Dominic is also here, maybe let me just make sure. So is that anomaly written in terms of some? These are 2+1D Fermi surface, but the anomaly is written as some 5D term. Is that right? And the anomaly evolving either 3 over U1 or maybe U1 gravity square type of anomaly. Is that the correct way to say that? And
it's the anomaly that involves the 5D Chern-Simons term. You can think of it that way.
Yes, but the Chern-Simons contain maybe part of a contribution from the momentum space gauge field and possibly also some spatial translation related to gravity. So
I mean, there's no gauge field for translations. So I mean, effectively the boson plays the role of the gauge field for the loop group symmetry. That's why the anomaly arguments come into play, but there's no gauge fields for other stuff, so you don't need to worry about those kinds of things.
I said the background gauge field, not the dynamic. The ADA.
Well, it becomes a dynamical gauge field in these critical Fermi surface problems because the boson effectively plays the role of a gauge field. But this, I mean, we're in flat space and everything, so you don't need to introduce background metrics or anything. That would be overkill.
So can you give an argument? What's the upshot of this, like, connect to conductivity, if you want to summarize, or maybe some of you want to summarize? Is this some non-trivial fact, or is it just some obvious?
I don't know if it's obvious. I mean, it's a particular feature of these models that it's not coming only from the emergent symmetry anomaly. You look at the particular Lagrangian and you can leverage. Yeah, I don't know how to say it in a few seconds, but
yeah, you should invite one of us to give a talk on this. It's pretty involved.
I do think I sent Dominic an invitation some time ago, but we should arrange again. Yeah. Okay, great. Thanks. Any more questions, comments? Okay. right? If not, we should thank Haoyu again. Thank you, Haoyu. Thank you for the great seminar.